Thank you. Good afternoon, everyone. And this talk is about routing Android. So a little bit about us. My name is Zhenpeng. I have a PhD from Northwestern University. I specialize in kernel security. And Xing is my advisor, who is an associate professor at Northwestern University. Zhaofeng, Chen, and Kang are from CERTIC. Zhaofeng is the principal researcher, and Kang is the chief security officer. So we are going to talk about IOU ring. What is IOU ring? IOU ring is designed to allow efficient asynchronous I/O operations. It provides a way for applications to create I/O operations without the need to interact with kernel constantly, which can improve performance and scalability. With IOU ring, applications can batch their submissions into the submission queue and fetch their completions from the completion queue, which reduces the overhead involved with system costs. And this IOU ring is a relatively new functionality in kernel, so it's still under very active development. And all this sounds pretty good, but IOU ring is actually very bad for security. And this is a tweet posted by Zhaofeng, who organizes KCTF VRP. Why IOU ring is so bad? It turned out that IOU ring is very buggy. It's under very active development, but at the same time, it's very vulnerable to attacks. If we check out the bug reports on Sysbot, just in the fixed bug category, there are more than 160 reports that has been fixed. And you can also find more bugs in the open category, and probably some of the bugs are still exploitable but not fixed yet. And with so many bugs, the exploitation against IOU ring is also very active. Those are some of the write-ups about exploiting IOU ring bugs. We have write-ups posted by Flash Security, a very beginning write-up on exploiting IOU ring, and a write-up from Starlab disclosing a new exploiting technique to the new bugs, to the new IOU ring. And we also have put an IOU ring on it, exploiting the Linux kernel from Choppy. This write-up and the one from Avaru and PQL has very detailed description of how IOU ring works. And also we have a write-up, a journey to the dawn posted by Kyle, which describes an IOU ring bug that is very similar to the one I'm going to talk about today. And we have a write-up about applying dirty crack technique in exploiting IOU ring bug. I believe there are more other write-ups that are not included here, but the thing is, the rich resource of exploiting IOU ring bugs drives more people into finding IOU ring bugs and exploiting them. In June this year, Google posted a blog about the lessons learned from the submissions to KCTF VRP. And the statistics show that as of June 2023, 60% of submissions targeted IOU ring, and around $1 million were paid to those bugs. So from the write-ups and the submissions to KCTF VRP, we see that how active the exploitation against IOU ring is. And at the same time, all the public exploits targeted desktop Linux kernel. And to mitigate the active exploitation, Google disabled IOU ring subsystem on Chrome OS, and there are servers on production. And for GKE Autopilot, they are investigating if they could disable IOU ring as well. And for Android, they have taken some measures to restrict the access to IOU ring. Those measures include using seccomp to fill out IOU ring syscalls from the sandbox, and using SLinux to limit the access. But it's still accessible from privileged contexts, for example, ADB or some system service. So we could still attack Android kernel with IOU ring bugs, because there are just so many bugs. There are a lot of potential for hackers. And exploiting Android kernel could be fun and profit. Google claimed to reward up to 250,000 US dollars for kernel privilege escalation exploits. But sadly, we don't have any public write-up about exploiting IO urine bugs on Android. So today's talk is about how I pawned the Android kernel with an IO urine bug. This is the CV number of the bug. There's no difference than any other IO urine bugs. You just interact with the IO urine subsystem, and you can somehow trigger a very stable invalid-free. Luckily, it's very stable. And I used this bug to pawn Google Pixel 6 and Samsung S22 in last year in 2022. And the bug was quickly fixed on July 29th after I reported the bug. So a little bit background to understand the bug. One of the great things of IO urine is that it supports asynchronous IO operations. You could submit different requests to the submission queue, and each request could be consumed and executed by kernel asynchronously. So the kernel will help you execute requests in the background, reading, writing files, sending message, and so on. Since it's done by kernel, so there should be something to prevent the privilege escalation. And to properly manage the privileges and the access control, each request will have like its own identity. And this identity represents the privilege of the process that's submitted in the request. And when kernel helps you execute the IO operations, you will use the identity the process provided to represent the privilege. So let's look at the implementation. This identity is stored in a structure called IO urine task, which contains a nested identity structure and an identity pointer. The kernel, by default, will use this nested identity structure, and it will initialize it first. And this identity pointer will reference to the nested identity structure. The design helps reduce memory fragmentation, so you don't have to allocate new heap memory for the identity. Instead, you can just reference the identity pointer to the IO urine structure itself as static memory. And the identity task structure is task specific, so it's referenced by the task, so that every time you can find the IO urine through the task structure. The identity has a mechanism of copy on write. So if the identity changes, meaning something like you change your UID by set UID or enter a new namespace, the identity for IO urine will need to be updated as well. And at this time, a new identity will be created through heap allocation and being initialized with updated process information. And this is the illustration of how the memory layout looks like. The identity pointer will now reference to the new identity on heap. This code snippet shows how kernel updates the identity. And this is where the bug happened. The IO urine task structure is retrieved from current task. And then it checks if the identity in the IO urine task and the requests are referencing to the nested structure. If it's true and the reference count becomes 0, the memory will be key-freed. Just like the comment showed here, this part tries to drop the identity reference count if it's from the heap. And the new identity, which is the ID variable here, will be assigned. All this looks fine, right? Remember that the identity is designed to support asynchronous I/O, and the request here represents a request submitted by a task previously. The question is, what if the request is submitted by one thread and the copy on write is done through another different thread? In this scenario, the IO urine task object, which is a tctx variable here, is from a different task than the requests. Then the condition here could be false, just because the identity never changed, and it's not from the heap. because the request is submitted by thread A, so its identity is actually thread A's nested identity, which doesn't reference to thread B's nested identity. So the condition here could be true. And if the reference count becomes 0, the K-free will free the thread A's nested identity, which is the IO task object. And this is how the bug happens. The figure here illustrates the memory layout when this invalid free happens. By freeing the identity, the kernel will free the IO task of thread B in the middle. And it's in the kmalloc 256 memory cache. And that's a memory corruption capability we obtained from the bug. How do we exploit this bug on Android? Doing kernel exploitation on Android is not easy. We have much more restricted access on Android. We don't have user namespace, so a lot of objects behind the user namespace is not available. We don't have views, user fault FD, so techniques rely on those two mechanisms is not useful. We don't have commonly used message or key or user key payload objects like we have on desktop Linux. In short, the choice of syscalls that could be used for exploitation on Android is very limited. The good thing is we have pipe subsystem on Android. And the pipe subsystem, for the pipe subsystem, we have an object called pipe buffer, which is an elastic object. It's good for spraying because it fits in different memory caches. Of course, it fits in a kmalloc 256 in this case. On the other hand, pipe buffer contains a global pointer, OPS, which is good for leaking, so that we could bypass KSLR through this global address. So with pipe buffer, we can turn this use of the free on identity to a user free on pipe buffer. To do that, we could trigger the invalid free, which will free the IO task object in the middle. And we will have the memory layout like this. The red box here means the memory region is freed. Then we spray the pipe buffer in the cache, which will reclaim the memory area of this identity object. And the allocated pipe buffer will start in the middle of the IO task object. And after this, we free the IO task, which frees the pipe buffer partially. And now, the intersection of the red box and the green box here is the use of the free memory on the pipe buffer. So we have the use of the free on pipe buffer. How can we leak it out to bypass KSLR? Is there any specific kernel objects that could help us do that? I tried to search the whole kernel and didn't find anything helpful. And suddenly, when I look back at the IO design, an idea came out. Just to recap a little bit, so to enable the efficient IO operations, the IO ring used a ring buffer to transport data between user space and kernel space. That means the kernel could access to the user space memory. How does it work? We have protections from hardware like SMAP or PXN that prevents kernel from accessing user space memory. It turns out that this ring buffer is a piece of memory that is mapped to both kernel and user space. It's shared. The memory is allocated through the body allocator in kernel and is mapped to the user space so that the data transportation could be done without copy to user or copy from user. And the kernel and user space could read and write the memory from each other directly. This design is interesting. One question is, if the page mapped to user space is recycled with the freed page from the slab allocator, it turns out some pages are, and they are recycled with each other. So that means we can reclaim the freed slab page by spraying user pages. In the past, to manipulate heap memory, people use techniques of spraying kernel objects. Now we can just spray pages, and we can read and write kernel heap from user space. There are some candidates, they are very easy to use on Android. For example, the IO shared rim buffer, the pages in a pipe subsystem, and we call this page spray technique dirty page. The advantages of spraying pages are very obvious. First, it's very powerful. We could just directly read and write the kernel heap from user space. Second, it's very stable. In the past, we have to spray several times to obtain different read and write capabilities to some victim objects. Now, we can just spray once, and it could get unlimited chance to read and write on those victim objects. Third, it's very simple. You can just allocate more, and the body allocator will help you reclaim the page for you. So with the dirty page technique, we could easily achieve arbitrary read and write on the pipe buffer object. To do that, we first prepare the memory layout like this. We have a pipe buffer allocated in the same cache of the identity and the IO task. Then we trigger the invalid free and free the IO task. This invalid free indeed is an additional free to the slab, because normally there isn't such a free to the object. And this one additional free will be counted by the slab allocator. As a result, after we free the other objects on this slab, even if we have a valid pipe buffer on the slab allocator still thinks there is no object alive, and eventually it will freeze the slab page. Then we apply the dirty page technique to reclaim the slab page and map the memory in user space. Here we use the page in the pipe subsystem. As such, we can have arbitrary read and write capability on the pipe buffer. What can we do with this capability? Let's look at the definition of this pipe buffer object. If we have read capability, we could leak the OPS field. This is a global pointer in kernel. By leaking it, we could bypass KSR. On the other hand, we could also overwrite the pipe buffer. The first field that is interesting is the flags. By overwriting these flags, we could have dirty pipe retro, because the root cause of dirty pipe is due to the uninitialization of this flag. But this is not a key point of today's talk. Let's look at other fields. The page field, it seems suspicious. Can we achieve arbitrary read and write by overwriting this? Let's look at how pipe uses this page. From the two functions, pipe read and pipe write, we can see that this page is mapped to kernel first. Then the data from user space is copied in and out from it. What does this K-map do? It turned out that it just disables preemptions and page fault, then retrieve the virtual address from the page. And this page to virtual address calculation is static on ARM. It does some arithmetic shift on the page, then plus an offset. Both the shift and offset are static value on ARM64. So given a kernel address you want to read and write, you could calculate its page address with this function. Then you need to calculate the offset of the address to the base page. Then you can forge a faked pipe buffer with tempered page address and offset. And eventually, you can achieve arbitrary read and write by just reading and writing to the pipe. OK, demo time. This is a demo of how the exploit works for Pixel 6. The exploit obtains arbitrary read and write capability first, then overwrites the correct UID field of current process to escalate privilege. So with arbitrary read and write, escalating privilege in Pixel 6 is easy, just overwriting the UID of the CRUD. But for Samsung, it has its own customized protection, like KNOX. KNOX has a mechanism of protecting the CRUD's integrity. This is what a normal kernel CRUD looks like. It has a UID field, and simply override it could allow you to become root. And this is Samsung's CRUD objects definition with KNOX protection. It expands the original CRUD with some pointers to protect the CRUD integrity. One thing that's worth mentioning is that it has a field called the task pointer. So the CRUD will look like this. With the protection, the CRUD object is read-only, and only privileged instructions could alter its content. In addition, the task pointer in the CRUD object is used to do cross-check, which ensures the integrity. So you cannot just change the CRUD reference in the task to a root CRUD. This integrity check is done at the syscall entry, so it looks like there's no time window issue. One idea to bypass it is to forge a faked root CRUD with the UID being 0 and all the other pointers set up properly to bypass the integrity check. Does KNOX have any mechanism to prevent it being forged? It turned out that KNOX has a mechanism. And the function is KDB protect address here is to check if the CRUD is from a legit memory region. It checks if the memory is from the protect region by checking the object is from some specific cache. For example, here is checking if the object from the CRUD jar read-only or tsec jar / cache. As I mentioned before, this memory region is protected by KNOX, which is read-only even to root users. And this check is actually very weak because the page memory is not protected by KNOX, which means it's readable to attackers. We could just temper the /cache pointer in the page to confuse the kernel that a forged CRUD is from protect /cache. As such, we can bypass the whole CRUD protection. This is an illustration of how to bypass it. So to do that, we first forge a root CRUD with all pointers being set up properly. Then we find the page of the forged CRUD and temper the /cache field to CRUD jar read-only or tsec jar cache to bypass the check. Here's a demo for escalating privilege on S22. It's similar to the Pixel 6 one, but just some differences in overwriting the CRUD object. So in this talk, we went through the details of how we exploited an I/O urine box in the Android kernel with the page spray technique called dirty page. Here are some takeaways. First, I/O urine is a huge attack surface, not only to the desktop Linux, but also mobile devices. We have seen a lot of bugs found from this subsystem, and there will be more as it becomes more complex. Second, due to the huge attack surface, I don't think restricting access to the I/O urine on Android is enough to protect users. Attackers could still exploit the bug from privileged contexts, and I would not be surprised to see more exploitation to Android kernel with I/O urine bugs. Third, from the technique perspective, object spraying is not the only exploit option. try page spray in the future. And you will have more control over the kernel heap memory, like arbitrary read and write to kernel objects from user space. And lastly, as we have shown in the talk, the Android kernel exploitation with 30 page is simple. So don't be afraid of exploiting Android kernel if you found any bugs. And I hope we will see more interesting exploitation to the Android kernel in the future. One more thing, you can find exploit code from the link here, and the middle is my X handle, and the link below is my personal website. Feel free to reach out if you have any questions. I hope everyone enjoying the rest of your day, and now I'm happy to take questions.
So how likely is it for Android to disable IOU ring, just like the desktop? What prevents them from doing so?
I'm not quite sure, but I think probably they are using, like some system libraries are using IOU ring by default, so I don't know, probably Google can answer this question. I hope it will be disabled in the future until it's like mature, it's like there's more bug being found, it becomes secure. Yeah. All right. I think I will be here if you guys have any questions. If not, that's it. Thank you.